Okay, buddy, we're back. So this time we're going to be talking about Bernoulli's equation. Now, if you're confused and saying, well, didn't we talk about that earlier? We mentioned it. I gave it to you. But last time we just kind of said, it works. And that's not enough. We know it works along a streamline, but let's actually derive it. So today we're going to derive this. Okay. Now, first off, let's actually start off with what it looks like. Remember, it was the pressure plus 1/2 my density times my velocity squared is equal to a constant. And we know it works along a streamline, but will it work anywhere else? I'll have to find out. And this is like the most famous experimental equation. Like if you're doing experimentation, this is super, super important, okay? If you're doing simulations, it doesn't really matter because you just look and see what the pressure or velocity values are. You just pick a number or pick a spot and you get it. Now, just like last time, we had assumptions we were talking about that were important, like incompressible and viscid. For this equation, we also have assumptions. So let's figure out what those main assumptions are going to be. So main assumptions right here. Yep. And what are they? Well, they're a lot, okay? First off, we're assuming it's inviscid. Okay, so that means we have very low, small velocity gradients, or they're not there at all. We assume it's incompressible. We're going to assume that we have no body forces. That it's steady. And that it's along a streamline. As a note, there are some cases where it doesn't have to be along a streamline, and we'll get to that later. And just in case you forgot, inviscid says that the viscosity is equal to 0. Incompressible, density is equal to a constant. No body forces is saying that term, that our density times our acceleration is equal to 0. Steady, all of our time derivatives go to 0. And along a streamline, well, that's along a streamline. There's our streamline, and we're picking a point right here and right here when we're doing our Bernoulli's equation. So in this case, I would have P1 plus 1/2 rho U1 squared would be equal to P2 plus 1/2 rho U2 squared. Why does there no 1 or 2 next to the density? Because it's constant. Don't forget that. Okay, so these are important for us. Let's not forget them because we're going to need those later. And I'm going to go ahead and box this in because let's keep it nice and safe. Beautiful. I like it. Now, let's derive Bernoulli. So we're going to start off with our full-out conservation of momentum equation, and then we're going to simplify it just like those assumptions said, and things are going to get pretty easy from there. Okay, so derivation begin. So we'll do this for the x direction. Why? Because it doesn't honestly matter too much. It's more or less the same equation each time. And we'll have our density times du dt plus u du dx plus v du dy plus w du dz is equal to negative dp dx, be very careful with this, plus our viscosity times second derivative of the position of our x component velocity and the x, y, and z directions. As a note, this gradient squared thing, that is actually called the Laplacian. It's going to be a lot easier if I go ahead and tell you that so I can say the Laplacian of it each time. Otherwise, it takes longer to say. Okay. Beautiful. Oh, and plus the body forces, which just did not even fill in the page, and we have it. So we already know that this whole term right here is 0 because we are inviscid. Nice. This one is also going to be gone because we have no body forces. And then the last term we're going to get rid of is this one right here, because we are saying it is steady. Now, if you looked at my conservation momentum earlier, you didn't actually see this term because this was my total derivative. Okay, that is the total derivative that we saw earlier, the big D dt. So just know that's where it came from. It's not just a magical thing that it suddenly appeared. We had to break it apart because we're going to do this. Now, if I've done that, I can already simplify this dramatically. And what I get, I'm not going to write it 3 times, but I could. It's something like this. What I'm going to do is I'm going to write it in black. I'm going to write the things that can change in red so you can see what the difference in the equation is. And I'm just going to write it for the x component again. So it's simplified down to something like this. Density times my velocity times the velocity gradient in the x direction. Whoop, I'm already failing at this dramatically. I'm going to leave that guy off. There we go. Okay, and so I have u right here, and I have x right here. And just know that x could be either equal to x, y, or z, and that u could be equal to u, v, or w, and all those would be connected for either the x, y, or z components. Okay. Now, I can turn these into vectors. Vectors make things a lot easier. So what I'm going to do is I'm going to make 2 vectors here. So first off, let's see here. I'm going to call the position, I'm going to make that s. So s is going to be my position vector. I'll have that be x, y, and z right here. And then we'll have our velocity, which I'll just make a kind of like fancy u, is equal to the u, v, and w. Now, if I write it this way, I can then make my Bernoulli equation look a lot simpler. So let's go ahead and make it look a lot simpler because things will be really nice then. So if I do that, and I assume, okay, this is along a streamline. Okay, pen's being a bit weird there. There we go. Along a streamline. Okay, so if it's along a streamline, then we know the following is true. It will look something like this. So I would have rho times my fancy u, which is just bringing all my components of velocity together. I'm going to have my du ds. Okay, so it's going to change with position. There we go. Fancy u. Beautiful. Is equal to how my pressure changes with position. Now, I see ds on both sides, so I cancel them. Gone. And I have then, I can integrate. I have my integral of rho u du is going to be equal to negative my integral dp. And if I do that, I get a pretty easy integral, which simply says that 1/2 rho u squared, make sure I do it right, there we go, is going to be equal to my pressure plus a constant. Or, since this is, I can put all on one side, I can then say that my pressure plus 1/2 rho u squared is equal to a constant. And as a note, reminding you, that's along a streamline. So at the beginning, I'm saying it at the end. Okay, now, is this the technical derivation? No, honestly it's not. It's a longer one. And I'll show you in the next video, but this is a really simple way of showing how we get to that, okay? So, this is not, let me put it in red. This is not the technical derivation. It's the simple one. But next time we'll see the technical one too, okay? And if you don't want to see it, you can skip it. Well, that's it for this time. So we saw how Bernoulli's works, we saw where it comes from, we saw how we get that equation from our conservation of momentum. And you already know that it's incredibly important for experimentation. So next time I'll show you a much more exact derivation for how we get it, and we'll go from there. Have a good day. Bye-bye.